Hi, my name is Ivelin Georgiev, and I'm a PhD student at the Department of Astronomy at Stockholm University. Today, I would like to present to you my work on the impact of the mean free path effect on the large-scale 21 centimeter power spectrum. I would like to give a brief overview of this talk, which follows the paper itself. I firstly study a decomposition of the large-scale 21 centimeter power spectrum into the cosmological density and neutral fraction fields. I then proceed to discuss how the mean free path of ionizing photons affects the shape of the large-scale 21 centimeter power spectrum in simulations of reionization, and lastly, I investigate this effect by actually biasing the 21 centimeter power spectrum. So, as a brief overview, the early universe after the emission of the CMB primarily consists of neutral hydrogen, which can emit radiation via the 21 centimeter hyperfine transition. The Epoch of Reionization is a period where the first stars and galaxies form and release ionizing radiation into the intergalactic medium. This radiation will reionize the neutral hydrogen within the IGM and remove the 21 centimeter signal. One method of studying this process is by examining the power spectrum itself. It's important to note that the Epoch of Reionization marks the last known phase transition of the universe, from a neutral to an ionized state, and it encompasses a large dynamic range of physical processes. These are the project aims and motivations. They overlap with the first slide, but it's worth pointing out the motivations itself. Radio interferometers such as SKA are very well attuned to studying low K scales, which correspond to large physical scales. And the low K scales themselves should be simpler to understand as they average over various astrophysical processes. So, to better understand the behavior of the large-scale 21 centimeter power spectrum, we decompose it using the formalism described with Litz et al. And you can see this decomposition color-coded at the top. In the plot below, we divide each term by the signal itself, the one seen in black, and we study the fractional contribution of each term at a fixed K-scale of 0.1 inverse megaparsec during the epoch of reionization. The take-home message is that the 21 centimeter power spectrum is dominated by the density term early on, seen in red. The signal equilibrates at a globally averaged neutral fraction of around 0.88, so the universe is about 12% ionized, after which the signal can be described using the neutral hydrogen autocorrelation, so the blue term, and the cross power spectrum, the green term. The high-order terms play less significant roles throughout the epoch of reionization, gaining importance during very specific periods, such as the equilibration and the end of reionization. To reiterate, prior to equilibration, the 21 centimeter power spectrum is dominated by the density autocorrelation component, so the one seen in red. After equilibration, the 21 centimeter power spectrum is dominated by the neutral hydrogen autocorrelation component, so the one seen in blue. Armed with this understanding, we look at an example model of the 21 centimeter power spectrum at the midpoint of the epoch of reionization, so when the universe is half ionized. Even though the shape of the 21 centimeter power spectrum is defined by the neutral hydrogen power spectrum component, on large scales, it is a biased version of the cosmological density power spectrum. How does this occur? Well, we see that within the purple circle, there is a specific feature which is often associated with the characteristic scale of bubbles. It has also been discussed that it is related to the mean free path of ionizing bubbles. We hence shift focus and explore how this occurs in nature as well as in simulations. We define the mean free path as the average distance an ionizing photon travels through the IGM before it's absorbed. The two specific cases of this are defined below as A and B, and this figure from Keating et al. 2015 is a provided example of both of these cases. In case A, an ionizing photon is free to propagate to the edge of the ionized bubble and is absorbed by the neutral hydrogen within the IGM. Conversely, for case B, the ionizing radiation is absorbed by residual neutral hydrogen within the ionized region itself. In the case of large simulations of reionization, modeling case B is a difficult task due to the coarse resolution. Hence, methods of implementing the mean free path have to be considered. Often this is done by limiting the sizes of the ionized bubbles with the use of soft or hard barriers, which we'll discuss shortly. It's also worth pointing out that the mean free path is a measured observable from quasar spectra. As you can see, most observations are past the epoch of reionization, but the evolution of the quasar ionized regions that tell us about the mean free path tell us a lot about the state of the IGM at these higher redshifts. Note that the most obvious discrepancy between the interpolation of the post-reionization measurements against those of Becker 2021, so the ones seen in green specifically. This would suggest that at a redshift of 6, there might be more neutral hydrogen still lingering around and hinting at an extended reionization process. What we get from this is the mean free path plays an important role in the epoch of reionization, just as well as it is just as crucial in modeling the epoch of reionization itself. Hence, we need to think about it in more depth. So to better understand this mean free path effect, we investigate 4 simulations of box size 714 co-moving megaparsec with a fixed mean free path. We have 2 sets of simulations, where in the first set, one has a more larger value of the mean free path closer to the measurements which followed the implementation, so around 70 co-moving megaparsec at redshift 6, while the other one is more consistent with the lower value, so around 19 co-moving megaparsec, not too dissimilar from the Becker measurement. The other set of simulations that we have a fixed mean free path. However, the implementation itself is allowed to differ. In the previous set, it was a hard cubic barrier, which doesn't allow radiation to propagate further than the defined distance. In this set, the red model has a hard spherical barrier, while the yellow model has a gradual absorption barrier such that the optical depth at 10 co-moving megaparsec is equal to tau 1. It's also worth to update our approach in constructing the bias parameter so we can understand how this will affect the power spectrum. If the large-scale 21 centimeter power spectrum is a biased version of the density field, we expect the bias to be scale independent on those scales. Hence, we choose a linear bias and we add an additional parameter n that introduces some scale dependence. We formulate the bias in the following method to remove the contribution of the n parameter. So now we study the bias for the first set of simulations of the epoch of reionization, and note these were the ones with the varying mean free path size, but a fixed implementation. Early on, the bias is shown in dotted lines and is particularly flat and indistinguishable between models, as the mean free path has not made its mark. After the midpoint, so the midpoint of reionization, now dashed line, it already tells us something about the bubble size distribution, as the scale-independent regime has shifted to lowercase scales, and the uniformity suggests that the peak of the distribution is similar between both models. However, the model seen in purple with the larger mean free path already seems to be telling us that there are larger regions which are slightly boosting the bias. Later on, so the solid lines, the differences in the k-dependence is visible for both models due to their mean free path constraints. Taking this empirical formula for extracting the k-scale of the break between the scale dependence and the scale independent regime, it tells us that it's very much related to the mean free path constraint we put in. The sharp break from the scale independence gives us 2 insights. Larger scales can be used as probes of cosmology with a scale independent bias, and the break itself tells us something about either the mean free path or the characteristic scale of the ionized bubbles. However, in our physical universe, the transition might be much smoother. So this is why we consider the other set of models. And if you remember, as I said before, one has a spherical hard barrier and one actually has a gradual soft barrier. In both cases, we fix the value of the mean free path to 10 co-moving megaparsec, but we only vary the implementation. And the differences are most visible at the later stages of the epoch of reionization, seen in the solid lines. The transition starts earlier for the gradual transition model, so the one seen at yellow already at the midpoint, and extends to lower k scales despite the barrier. This is because the soft barrier is such that even at an optical depth value of tau equals 1, radiation is still allowed to propagate, and so even if it is a small amount, regions manage to overlap or grow a bit more, producing larger bubbles, smoothing out the transition and boosting it. So, just to conclude and summarize, after the first 10% of the universe has been ionized, the 21 centimeter follows the neutral hydrogen power spectrum. However, on large scales, it's a biased version of the density power spectrum. The transition of the mean free path value can be seen in the bias of the 21 centimeter power spectrum, and we've related it to this empirical formula. However, the shape of the transition depends on how the mean free path effect is modeled in simulations of the Epoch of Reionization. And if we were to take the Becker measurement of the mean free path and perform the same analysis, this will give us a good indication of which low K scales actually could be used as a cosmological probe of the matter power spectrum. And thank you for listening. I'll be happy to discuss this with you more live.